Lecture 1.2 Significant Figures. Exact numbers are numbers with defined values or counting numbers which are free from uncertainty. Examples are any counting numbers, definitions, for example, 1 dozen equals 12, conversion factors generally within the same system, such as 3 feet equals a yard in the imperial system, or 1 kilometer equals 1,000 meters in the metric system. In addition, all prefixes used in the metric system are considered exact conversions. There are, however, two other conversions between the English and the metric systems that are exact, although they do not appear to be so. These are done by definition. The first is 1 inch equals 2.54 centimeters. That is an exact conversion. Also, 1 calorie is 4.184 joules, which is an exact conversion of energy. Inexact numbers are numbers that are obtained by means other than counting or by definitions. Examples are laboratory measurements, most conversion factors between systems, such as 1 pound is 453.6 grams. The two exceptions that we had before, for 1 inch equals 2.54 centimeters and 1 calorie equals 4.184 joules, are still definitions and are still therefore exact numbers. Significant figures are used to express inexact numbers and to report the uncertainty in a measurement. The last digit in a measured value is an estimate. That is, it has a level of uncertainty and is considered a significant figure. In the three examples that we have below, there are three different measures of uncertainty. In the first one, seeing how the meter stick only measures from 0 to 1 meter without any divisions in between, the approximate length can only be one more significant figure other than the 0 or 1 that is measured by the stick. In B, the measured length is between 60 and 70 centimeters. We can guess down to 1 centimeter on this. So the estimate here is 61 centimeters or 0.61 meters. And then finally, in part C, note that the end of the stick is between 60 and 61 centimeters, giving an estimated length of 0.607 meters. Counting significant figures. First, any digit that is not a 0 is considered significant. Second, zeros between non-zero digits are also considered significant. In this example, 606 meters has 3 significant figures with an uncertainty of plus or minus 1 meter. Zeros to the left of the first non-zero digit are not significant. These are used for us to have place value. In this example, 0.08 liters only has one significant figure. The 0 before the decimal and the 0 after the decimal are not considered significant, as they are just placeholders. All zeros to the right of the last non-zero digit are significant if there is a decimal point. In the first example, 2.0 milligrams, there are 2 significant figures. In the second example, 0.00420 grams, there are 3 significant figures. the first three zeros do not count. Only the zero at the end, after the 2. In the third example, we only see 2 significant figures. 93 million, the zeros are to the right, however there is no decimal to designate significance of those zeros. In order to do that, we would have to change this number from the standard form to the scientific notation to designate numbers in order to designate 93 million with a different level of significance, let's say 3 or 4 significant figures, we'd have to change the number to scientific notation. So for example, if we wanted 4 significant figures, 9.300 times 10 to the 7th would be the appropriate designation for 4 significant figures. Well, let's practice counting significant figures. In the first example, how many significant figures? The 3 is significant, the 4 is significant, and each of the 5s is significant, giving that a total of 4 significant figures. In the second example, the 3 preceding zeros do not count as significant digits. So only the 5 and the 8 count, giving 2 significant figures. In the third example, the 1, the 2, and the 5 definitely count. The 0 is sandwiched between the 2 and the 5, therefore it also counts, and there are 4 significant figures. In the fourth example, 250, since there is no decimal, this last 0 does not count as a significant figure. So only the 2 and the 5 count as significant figures, so there are only 2. Lastly, 250 milliliters at the bottom has 5 total significant figures because the 3 zeros at the end count. They count because there is a decimal in the number. So there is a total of 5 significant figures. Rounding. If the first digit to the right of the last digit to be retained is less than 5, then we round down, leaving the retained digit unchanged. However, if the first digit to the right of the last digit to be retained is greater than or equal to 5, then we round up, adding 1 to the retained digit. So let's round each of the following numbers to 3 significant figures. 345.5, we're going to take the first 3 digits as significant figures, and trailing the 5 is 0.5, therefore this one gets rounded up to 346 centimeters. In the next number, we start counting significant figures at the 5. So the 5, the 8, and the 7 are the 3 significant figures. Cutting it off there will give us 0.00588 rounded up. Next one, 120.5. This has 4 significant figures in it, but we want to round it up to 3 significant figures. So the 1, the 2, and the 0 are our significant figures, but the 0 gets rounded up to a 1, so we have 1, 2, 1, 0. We do not put a decimal place after this, as that would designate this as having 4 significant figures. And finally, the 250 milliliters rounded to 3 decimal places. We're going to end up cutting off the 2 zeros, and we end up with 250, but we have to put a decimal place at the end of this one in order to designate that there are 3 significant figures. When manipulating numbers, the mode of operation will tell us how to count significant figures. What we are looking at basically is a way of estimating the amount of error that is transferred in the numbers as we do mathematical calculations. In multiplication and division, the number of significant figures in the result is set by the original number that has the smallest number of significant figures. So in this example here, 4.51 has 3 significant figures, while 3.6666 has 5 significant figures. Since 3 is less than 5, our answer will have 3 significant figures. So if we start counting at the 1, the 6, and the 5 are our 3 significant figures. And with a 3 after that 5, we just drop the rest of it. And our number is now 16.5 to the appropriate number of significant figures. Division works exactly the same way, seeing how it's the inverse operation of multiplication. So we're looking for the smallest number of significant figures in division. Here we have 6.8, which has 2 significant figures, and the 112.04 has 5 significant figures. So our answer is only going to have 2 significant figures. The 0 does not count as a significant figure. Neither does the second 0 count as a significant figure. We start counting at the 6. So 6 and then 0, and then we cut it off there. Since the next number is a 6, we round this up to give the final answer of 0.061, which has 2 significant figures. Remembering that the first 2 zeros are just placeholders. In addition and subtraction, the error occurs in the last digit based upon place value. And the last digit with the highest place value determines the place value of the answer. So for example, if we take 89.332 and add 1.1, we get 90.432. The first number has place value that is 3 decimal places over. The second number has place value that is 1 decimal place over. Therefore, we cut this off at 1 decimal place, because the amount of error in 1.1 is much greater than the error in 89.332. Similarly, in subtraction, we take and look at the place value. The place value of 3.70 is here at the 100th point. The place value of 2.9133 is at the 10,000th point. So 3.70 has greater place value error in it, and therefore we will take and round off our answer to 2 digits, that is to the hundredths place value, which is 0.78 rounded up because there's a 6 after the 8 for a final answer of 0.079. Finally, when combining rules, doing multi-step calculations with addition and subtraction and multiplication and division also, the calculations with addition and subtraction should be done first to determine place value error, and then the multiplication and division done second in order to properly calculate the number of significant figures. We also have to follow the order of operations if there are any parentheses as part of the calculation. In this calculation below, 4.83 goes out to 2 decimal places. Therefore, the answer that you would get from this first initial subtraction is 1.274, but it should only go out to 1.27, having 3 significant figures. Those 3 significant figures are then carried through the calculation because the next number, 65.02, has 4, and then 112.04 has 5 significant figures, and it was the subtraction at the beginning that had the fewest number of significant figures after the subtraction was done, and that is 3, leaving us with an answer of 0.0739. If you had cut off the 4 and just left it at 1.27, what you get is an early rounding error, and that early rounding error would give you an answer of 0.737, which is slightly different from the number that we would consider a more accurate number.